Good morning, good afternoon, or good evening, everyone. We are going to be talking about infiltration. In this lecture, we're going to discuss the definition of infiltration, factors affecting infiltration, infiltration measurements, the Horton's model and Phillips equation, the Green-Amt model, ponding time, and fitting infiltration models to infiltration data using Excel. We're going to get to them in a while, but first we will begin with definitions of infiltration. So what is infiltration? It is the flow of water into the ground through the soil surface from rainfall or irrigation. In this scenario, percolation or soil water movement occurs. It is the process of water flow from one point to another within the soil. Infiltration and percolation play a key role in surface runoff, groundwater recharge, evapotranspiration, soil erosion, and transport of chemicals in the surface and subsurface waters. Before we move on, let us define the said terms. Surface runoff is basically nothing more than water running off the land surface, and one of its causes is precipitation. Groundwater recharge or deep drainage is a hydrologic process where water moves downward from the surface water to groundwater. Evapotranspiration or ET is an important part of the water cycle. It is the sum of water evaporation and transpiration from a surface area to the atmosphere. And soil erosion, as we all know, is a naturally occurring process that refers to wearing away of a field's topsoil by water and or wind. When water is applied at the surface of the soil, 4 moisture zones can be identified. Now I will show you a figure that describes the distribution of soil moisture in the infiltration process. The first zone where a thin layer of saturated zone is created is called the saturation zone. Beneath the first zone is called the transition zone. It is the transition zone. And the next lower zone is called the transmission zone, where the downward motion of the moisture takes place. Sa zone na to, unsaturated at consistent ang moisture content, wherein ang moisture content is above field capacity but below saturation. Ang last zone naman is called the wetting zone, kung saan ang moisture ng soil dito ay near field capacity at bumababa ang moisture content habang lumalalim. Tapos, ang boundary naman ng wetting zone, ang tawag wetting front, dyan nagkakaroon ng discontinuity between the newly wet soil at ng original moisture content ng soil. Depende sa amount ng infiltration at physical properties ng soil, pwedeng ma-extend ang wetting front from a few centimeters to meters. The infiltration process can easily be understood through a simple analogy. Now, consider a small container covered with a wire gauze. If water is poured into the container, a part of it will go into the container and a part overflows. Further, the container can only hold a fixed quantity. Kapag napuno ito, wala nang flow na mangyayari sa container. Now, this is a very simple analogy. The next analogy that I will show you highlights the maximum rate at which the ground can absorb water, or the infiltration capacity, and the volume of water that the ground can hold, or the field capacity. It is schematically modeled in this figure. Now, in this analogy, we can see that it is separated from low-intensity rainfall to high-intensity rainfall. Now, dito sa low-intensity rainfall, we can see that as water is poured into the container, andun lang siya sa container since konti lang na amount ng water ang nalalagay sa container. Compare dito sa high-intensity rainfall, may water na nandito sa container pero since maraming tubig ang pumapasok, merong surface runoff na nagaganap. Tapos, pagbaba naman dito, makikita natin na may infiltration na nagaganap. Tapos dito sa low intensity rainfall, since konti lang naman yung water ang nailagay sa container, konti lang rin naman na water ang andito sa zone na ito. Compare sa high intensity rainfall, parang mag-overflow na siya. Since, again, maraming tubig kasi ang pumasok sa container. Tapos, makikita natin pagbaba, may percolation to groundwater na nagaganap. So, since maraming tubig, mapupunta yung water to groundwater flow. And compare naman dun sa low intensity rainfall dun sa kabila, there's very little to no contribution to groundwater flow. Now, let us move on to infiltration capacity. Again, it is the maximum rate at which a given soil at a given time can absorb water. It is designated as F sub P and is expressed in units of cm/h. It is 1 centimeter over Planck's constant. The actual rate of infiltration F can be expressed as F equals F sub P, where I is greater than or equal to F sub P, and F equals I when I is less than F sub P, where I is the intensity of rainfall. The infiltration capacity of a soil is high at the beginning of a storm and has an exponential decay as time elapses. The infiltration capacity of an area is dependent on a large number of factors. Some of them are characteristics of soil, condition of the soil surface, current moisture content, vegetative cover, and soil temperature, which we will be discussing in a moment. For the characteristics of soil, the type of soil, texture, structure, permeability, and under drainage are important characteristics under this category. When soils occur in layers, the transmission capacity of the layers determines the overall infiltration rate, and land use has a significant influence on infiltration capacity. We can also see in this figure the typical variation of the infiltration capacity of a soil with time. For example, makikita natin na ang wet clay loam ay merong high infiltration capacity sa una at bumabawas ito as time progresses. We can observe the same characteristics naman sa ibang klase ng soils, pero yung dry sandy loam, kung makikita natin, ay mabilis mabawasan ng capacity kesa sa wet sandy loam. One example is a forest soil rich in organic matter will have a much higher value of infiltration capacity under identical conditions than the same soil in an urban area where it is subjected to compaction. Sa surface of entry naman tayo, at the soil surface, the impact of raindrops causes the fines in the soil to be displaced, and these in turn can clog the pore spaces in the upper layers. This is an important factor affecting the infiltration capacity. Thus, a surface covered with grass and other vegetation which can reduce this process has a pronounced influence on the value of infiltration capacity. And lastly, we have fluid characteristics. Water infiltrating the soil will have many impurities. Ang turbidity ng water, especially the clay and colloid content, plays an important factor at itong suspended particles na to blocks the fine pores in the soil and reduce its infiltration capacity. Temperature of water pati contamination, they are factors kasi naapektuhan nila ang viscosity ng water, which in turn affects the infiltration rate. Now, let's move on to measurements of infiltration. Infiltration characteristics of a soil at a given location can be estimated by flooding type infiltrometers, measurement of subsidence of free water in a large basin or pond, rainfall simulator, and hydrograph analysis. flooding type infiltrometers are experimental devices used to obtain data relating to variation of infiltration capacity with time. There are two types. First one is the tube type or simple infiltrometer, and the second is the double ring infiltrometer, and they look like this. The tube type infiltrometer is a simple instrument consisting essentially of a metal cylinder 30 centimeters in diameter and 60 centimeters long, open at both ends. The cylinder is driven into the ground at a depth of 50 centimeters. Water is poured at the top to a depth of 5 centimeters, and a pointer is set to mark the water level. As the infiltration proceeds, dinadagdagan ang volume ng water by adding water from a burette para ma-maintain ang water level sa tip ng pointer. Since nagdadagdag ng water during different time intervals, the plot of the infiltration capacity versus time is obtained. The experiment is continued until a uniform rate of infiltration is obtained, and it may take up to 2 to 3 hours. The surface of the soil is usually protected by a perforated disc to prevent formation of turbidity and its settling on the soil surface. A major objection to the simple infiltrometer is that the infiltered water spreads at the outlet from the tube, and as such, the tube area is not representative of the area in which infiltration is taking place. Now, the double ring infiltrometer is most commonly used since it is designed to overcome the basic objection of the tube infiltrometer. We can see that there are two sets of concentrating rings with diameters of 30 centimeters and 60 centimeters and a minimum length of 25 centimeters. The two rings are inserted into the ground, and water is applied into both of the rings to maintain a constant depth of 5 centimeters. The outer ring provides a water jacket into the infiltrating water from the inner ring and hence prevents the spreading out of the infiltrating water of the inner ring. Mine-maintain din ang lalim ng tubig sa inner at outer rings during the observation period, pero the measurement of the water volume is only done on the inner ring. The experiment is carried out until a constant infiltration rate is obtained. Again, merong perforated disc na nilalagay to prevent the formation of turbidity and etc. Although flooding type infiltrometers measure the infiltration characteristics at a spot only, a large number of pre-planned experiments are necessary to obtain representative infiltration characteristics for an entire watershed. Some disadvantages are: 1. The raindrop impact effect is not simulated. Number 2, the driving of the tube or rings disturbs the soil structure. And 3, the results of the infiltrometers depend to some extent on their size, with the larger meters giving less rates than the smaller ones due to the border effect. The second measurement of infiltration is the rainfall simulator. A small plot of land about 2 by 4 meters is dedicated to this experiment. The specially designed nozzles produce raindrops falling from a height of 2 meters and are capable of producing various intensities of rainfall. The experiments are conducted under controlled conditions with various combinations of intensities and durations, and the surface runoff rates and volumes are measured in each case. Using the water budget equation, change in storage equals P minus R minus G minus E minus T, where P is the precipitation, R is surface runoff, G is net groundwater flow, E is evaporation, and T is for transpiration. Rainfall simulators give lower values than flooding types. This is due to the effect of the rainfall impact and turbidity of the surface water present in the former. And lastly, we have the hydrograph analysis. Reasonable estimation of the infiltration capacity of a small watershed can be obtained by analyzing measured runoff hydrographs and corresponding rainfall records. If sufficiently good rainfall records and runoff hydrographs corresponding to isolated storms in a small watershed with fairly homogeneous soils are available, water budget equation can be applied to estimate the abstraction by infiltration. In this process, the evapotranspiration losses are estimated by knowing the land cover or use of the watershed. Now that ends the first part of the report, we will now proceed with the Horton's model.
Good day everyone. Now that we have know the basic knowledge about the infiltration, we will now proceed to the different model proposed to compute for the infiltration rate or infiltration capacity. And we will start in the Horton's model, which is assigned to me. The infiltration process was thoroughly studied by Robert E. Horton in the early 1930s. Horton's equation is another viable option when measuring ground infiltration rates or volumes. Mr. Horton studied infiltration process for so many years, and he studied how it works, how a specific property of soil affects the infiltration rate, and many more that is connected to infiltration process. And the result of his work was the Horton's equation that we will be discussing in the following slides. Robert Elmer Horton, May 18, 1875 to April 22, 1945. Horton was an American civil engineer and soil scientist considered by many to be the father of modern hydrology. Now we will proceed for the Horton's equation that was made by Mr. Robert E. Horton. It is an empirical formula that says that infiltration starts at a constant rate F naught and is decreasing exponentially with time t. After some time, when soil saturation level reaches a certain value, the rate of infiltration will level off to the rate F sub c. So we have this equation proposed by Mr. Horton. F of t is equal to F sub c plus F naught minus F sub c multiplied to e raised to negative kt, where F is the infiltration capacity depth over time at some time t. F naught is the initial infiltration capacity or maximum infiltration rate. F sub c is the final infiltration capacity or equilibrium infiltration rate after the soil has been saturated, or minimum infiltration rate. K is an empirical constant that says something about how long it takes for rain to force a soil from its initial to its final infiltration capacity. And of course, the T is the time. And we have here a second equation from Horton that was made by Horton. The other method of using Horton's equation is as below. It can be used to find the total volume of infiltration F after time t. So we have here F sub t is equal to F sub c multiplied to t plus F naught minus F c or F sub c over k multiplied to 1 minus e raised to negative kt. So the first equation, we need to remember that it is used to get the infiltration rate, while this second equation that we have here in our screen is an equation to get the total volume of infiltration. In the next slide, we will have a sample problem. So we have the initial filtration capacity of watershed estimated as 1.5 inch per hour, and the time constant taken to be 0.35 hour raised to negative 1. The equilibrium capacity is estimated as 0.2 inch per hour. We have two questions here. Letter A, what are the values of F at t is equal to 10 minutes, 30 minutes, 1 hour, 2 hours, and 6 hours? And B, what is the total volume of infiltration over the 6-hour time period? So we will now first proceed with the question A. So solution. From the Horton equation, we have F is equal to 0.2 plus 1.5 minus 0.2 multiplied to e raised to negative 0.35 multiplied to t. And I already substituted the given values in the problem to the Horton's equation, or to the first equation given earlier. So 0.2 was the F sub c, or the final infiltration capacity, and 1.5 is the F naught, which is the initial infiltration capacity, minus the final filtration capacity. And e raised to negative 0.35, which is 0.35 is our k, which is the empirical constant, and t, which is the time. So we will now substitute all of the given time to t to get the value of f for each time given. We have already the given here, which is f naught is equal to 1.5 inch per hour, f sub c is equal to 0.2 inch per hour, and k is equal to 0.35 1 over hour. And our t, which is 10 minutes, 30 minutes, 1 hour, 2 hours, and 6 hours. Then we will just substitute all of the given numbers or values to our formula, or to the Horton's equation, which is f of t is equal to f sub c plus f naught minus f sub c multiplied to e raised to negative kt. So we have here in the solution f is equal to 0.2 plus 1.5 minus 0.2 multiplied to e raised to negative 0.35t. And we have already discussed how we substituted each of the variables in the equation, or each of the values of each of the variable in the equation earlier. So let's start with t is equal to 10 minutes. So for us to convert it to hour, we need to multiply it to 10 minutes equal to 1 hour over 60 minutes. So we will cancel the minute, the unit, and this will become 1, this will become 6. So 1 over 6 hours. So we have RT is equal to 1 over 6 hours. And when we compute for the value of f, when t is equal to 1 over 6, we have here f is equal to 0.2 plus 1.5 minus 0.2 multiplied to negative 0.35 t, or RT is already 1 over 6. So when we input that, or yes, this to our calculators, we have 1.43 inch per hour. So that's the value of our f when t is equal to 10 minutes or 1 over 6 hours. Next is when t is equal to 30 minutes. And like what we did earlier, we will convert first 30 minutes to hour, where we need to multiply 30 minutes to 1 hour over 60 minutes. So we'll cancel this and this. This will become 2 and this will become 1, where 30 minutes will become 1/2 hour. So we have 30 minutes or 1/2 hour. Then we will substitute 1/2 hour to our t in the equation given again. So f is equal to 0.2 plus 1.5 minus 0.2 multiplied to e raised to negative 0.35 multiplied to 1/2 hour. So when we input this again to our calculator, we have f is equal to 1.29 and inch per hour. We will stop here, for I think we already know how to compute for the value of f given the specific time. So, and I will just show you the answers when t is equal to 1 hour, 2 hours, and 6 hours here in the table that I've made. And substituting in values of t yields 1 over 6, which is the time, to 1.43, which is our f, or our infiltration rate, inch per hour. 1/2 is equal to 1.29 inch per hour. 1 hour is equal to 1.12 inch per hour. 2 is equal to 0.85, and 6 to 0.36. And we can see here the relation of these two, that when hour goes up from 1/6 to 6 hours, the infiltration rate goes down. So from 1.43 here, we can see that it goes down to 0.36. And next we will proceed to the second question, but before that, we have the table here on the previous page when plotted. It looked like this graph, and we can see here that the infiltration rate, which is this line, goes down when the time goes up. And you can see here that the shaded part shows the volume for 6-hour period, and this is connected to the question that we have in letter B. So now we will proceed for the question B. What is the total volume of infiltration over the 6-hour time period? So we have the given here, like from the previous question. F naught is equal to 1.5 inch per hour, F sub c is equal to 0.2 inch per hour, and our K, which is the empirical constant, is equal to 0.35 1/hour. Our formula is F sub T, or this is the formula to get the infiltration volume. F sub T is equal to F sub C times T plus F sub, or F naught minus F sub C over K times 1 minus E raised to negative KT. So to compute for the volume infiltration, we will use the knowledge that we have in integral calculus, specifically the topic definite integral. So we have here with the upper limit 6 and lower limit 0, 0.2 plus 1.5 minus 0.2 multiplied to e raised to negative 0.35 dt, or is equal to 0.2t, which is when we substitute the values given to the formula that we have, 0.2t plus 1.5 minus 0.2 over 0.35 multiplied to 1 minus e raised to negative 0.35t. And for us to get the total volume of infiltration over the 6-hour time period, we need to subtract the value of F when our time is 6, and minus to our the value of F when our time is 0. First, when t is equal to 6. So F of 6 is equal to 0.2, and our t is equal to 6 plus 1.5 minus 0.2 over 0.35 multiplied to 1 minus e raised to negative 0.35 t, or RT is equal to 6 for red. So we have 0.2 times 6, we have 1.2 plus this, it will be equal to 3.7143 multiplied to 1 minus e raised to negative 0.35 times 6, which is be equal to e raised to negative 2.1. Then when we add this and multiply this one, we will get the value of F when the t is equal to 6 equal to 4.46 inch. So F of 6 equal to this one. So we already get the F of 6, or when t is the value of F when t is equal to 6. Now we will get the value of F when t is equal to 0. So when t is equal to 0, we have here, we'll just do the same process earlier. So f of 0 is equal to 0.2 multiplied to 0 plus 1.5 minus 0.2 over 0.35, then multiply to 1 minus e raised to negative 0. Or raised to negative 0.35 multiplied to 0. So f of 0, we know that this will equal to 0 plus 1.5 minus 0.2 or 0.35, and we already know that it is equal to 3.7143, and 1 minus e raised to negative 0.35 times 0, and we know that e raised to 0 is equal to 1, so this will become 1. So 1 minus 1, we know that 1 minus 1 is equal to 0, and multiply to a number is will also equal to 0. So f of 0 is equal to 0. So when we get the or when we compute for the total volume of infiltration over 6-hour time period, we have f of 6 minus f of 0, and we get the value of f of 6, which is 4.46 minus 0. So the total volume over 6-hour time period is also 4.46 inch. So that's our final answer for the total volume infiltration over the 6-hour time period. The volume of water can be found by taking the definite integral under the curve from 0 to 6 hours, which we did earlier, where we get the definite integral of the first equation of the Horton model, and we have the second equation when we integrate it, having the upper limit 6 and the lower limit 0. Evaluating the right side for t is equal to 6, and then subtracting the values for t is equal to 0 yields an answer of 4.46 inches over the watershed. And that's all for Horton's equation. Thank you.
I discussed about Phillips' equation, but before that, we must first know the Darcy's law and other equations for us to understand Phillips' equation. Darcy's law is the earliest and most rigorous mathematical study of the phenomenon of vertical flows of liquids in saturated and unsaturated soils. Here's the equation of Darcy's law in saturated soil, where Q is the Darcy flux, H is the total hydraulic head, which is the sum of pressure head and gravity head, and K is the hydraulic conductivity. So Darcy's law was expanded by Buckingham, which is used for unsaturated soil conditions. In an unsaturated soil conditions, we have to deal with two gradients: the metric potential, which is the capillary and absorptive forces, and gravity. The total hydraulic head will be the sum of these two gradients. Simplifying this, we have Q equals to hydraulic conductivity times the derivative of metric potential with respect to space plus the derivative of gravimetric potential with respect to space. Now this one will be equal to 1, and distributing the hydraulic conductivity will get this. Now this equation here can be applied in steady state conditions. Steady state conditions mean that, for example, if you have a soil column the influx or the water that comes in and the outflux is equal. It means that the water content doesn't change. But in unsteady state conditions or transient flow conditions, that is not applicable, because in a natural environment, time is also a thing to be considered to solve for the flow. For that, we'll use the continuity equation, which is the derivative of water content with respect to time equals to the derivative of flow with respect to space. Substituting the value of Q that we have in the previous equation, we'll have this. Simplifying that, we'll have this equation, which is the Richards equation, the governing equation for unsteady and saturated flow in a porous medium. Now we'll go to Phillips equation, 1957A. For cases of vertical infiltration, Phillips' solution of Richards equation was of the form of physically based converging power series, which described cumulative infiltration as a function of time. So, cumulative infiltration equals to S times T raised to 1/2 plus the quantity of A sub 2 plus K times time, and so on. In Phillips equation 1957b, he further showed that a simpler form of the previous equation with just two fitting parameters is sufficient for all practical purposes to describe the time dependence of cumulative infiltration. Cumulative infiltration equals to S times T raised to 1/2 plus A times T, where S is the sorptivity, A terms the transmissivity, K is the hydraulic conductivity, and of course T, which is the time. The transmissivity term in the previous equation has dimensions LT raised to -1, which is the length and time, and reflects the cell's ability to transmit water under the influence of gravity. And according to Dunin, transmissivity term, or A, is related to the soil's saturated hydraulic conductivity. In Phillips equation 1969, Philip observed that for long intervals for which the infinite series of this equation does not converge, this equation can be approximated by cumulative infiltration equals to S times T raised to 1/2 plus K times T. Now this is the Phillips equation for cumulative infiltration. By differentiating that, we'll get the infiltration rate. The sorptivity term reflects the soil's ability to absorb water by metric forces during the initial stages of the infiltration process. For a horizontal column of soil, gravity effects are considered negligible, and the contribution of K times T term is also negligible. So the formula for cumulative infiltration in a horizontal soil column is reduced to this one. Now we'll have our example. A small tube with a cross-sectional area of 40 square centimeter is filled with soil and laid horizontally. The open end of the tube is saturated, and after 15 minutes, 100 cubic centimeter of water have infiltrated into the tube. If the saturated hydraulic conductivity of the soil is 0.4 centimeter per hour, determine how much infiltration would have taken place in 30 minutes if the soil column had initially been placed upright with its upper surface saturated. Before we solve for the cumulative infiltration in a vertical soil column, we must first find the sorptivity, because the given are just the hydraulic conductivity and time. For that, we'll use the Phillips equation in horizontal soil column. Cumulative infiltration equals S times T raised to 1/2. The cumulative infiltration is the water that have infiltrated over the cross-sectional area of the tube equals to S times time, which is in hour, raised to 1/2. Simplifying that, we'll get 5 centimeters times r raised to negative 1/2. Now we have the value of sorptivity. We can now solve for the cumulative infiltration in the vertical soil column. Cumulative infiltration equals S times T raised to 1/2 plus K times T. 5 times time, which is in hours, raised to 1/2 plus the hydraulic conductivity times time. Now we'll get a cumulative infiltration of 3.75 centimeters. So that's it. Thank you.
Next infiltration model is the green amp model. It is most useful model in estimating water movement in soil. This method derives an equation for total depth of infiltration. It was published in 1911 by Green and Amp, who did their work in Australia. We have these simple assumptions to this model. Capillary forces act at wetting front. Behind the wetting front is saturated. Soil water suction below the wetting front remains constant. The next thing we wanted to do is to calculate the rate at which the wetting front was moving. In the green amp equation, there's a lot of variables that goes into the equation. Big F of t is equal to the cumulative infiltration from time 0 until time t. Small f of t is the infiltration rate at time t. Suction head is the pressure that the water experiences as it's being drawn down through the soil. Delta theta is the increase in soil moisture during infiltration. K is the hydraulic conductivity. T is the time period during which infiltration occurs. S sub E is the effective saturation. Theta sub E is the effective porosity. Next is we have a table of parameters for porosity. Effective porosity, wetting front, soil suction, head, hydraulic conductivity. We're gonna go through the process of trying to calculate how deeply the water infiltrated by solving an example. Determine the infiltration rate after 1 hour on a clay loam soil with an initial effective saturation of 30% and infiltration depth of 2 cm. For the solution, the given in the problems are effective porosity equals to 0.309, suction head which is equal to 20.88 cm, K equals to 0.10 cm per hour, effective saturation equals to 0.30, F equals to 2 centimeters, and the time is equal to 1 hour. So we find that delta theta using the formula 1 minus effective saturation multiplied by effective porosity, which give you the value of 0.2163. To solve for the infiltration rate, use the formula of F of t equals to K multiplied to the quantity of suction head times delta theta over infiltration depth plus 1, which give you a value of 0.326 cm per hour. And that's all for this topic.
Panding time. A simple, accurate method to predict time of panding under variable intensity rainfall. So what is time of panding? Time of panding is a term used in hydrology and refers to the instance when the land surface becomes saturated from rain and panding of water occurs. The prediction of the time to panding following commencement of rainfall is fundamental to hydrology prediction of flood, erosion, and infiltration. Most of the studies to date have focused on prediction of panding resulting from simple rainfall patterns. Mm. Natural rainfall has the variation in rainfall intensity during its event. However, the various infiltration models are subjected to rainfall intensities that are higher than the infiltration capacity of the soil at a given location. Diskin and Nasimov proposed recently the infiltration model, which is a simple conceptual model and can express the relationship between rainfall intensity and panding time. So, panding time is the period from the beginning of rainfall from the occurrence of panding. This model can compute the variation of the infiltration capacity for constant or variable rainfall rates. A simple conceptual model is available for carrying out the storm water runoff analysis. So, about panding, we are all familiar about what happens when rainfall occurs. So we can notice that some parts of soil surfaces or land areas are panding or panded by water. It happens due to infiltration. It is the ability of the soil to hold water. Infiltration occurs when surface water enters the soil. The sponge soaks water until it can hold no more. So this is when panding occurs. Land surface starts to pand because the soil has already reached its maximum capability and can't hold water anymore. So yeah. When water is applied to the soil surface, it infiltrates until the application rate exceeds the soil limited infiltration rate. So when panding occurs at the soil surface, the runoff and erosion can be initiated. The ability to estimate accurately when initial panding occurs and how much runoff is produced is important in civil and agricultural engineering and is essential for the proper design of irrigation systems, rain harvesting reservoirs, and hydraulic structures at the level of watershed. Spatial and temporal variability in rainfall and water application rates also affect infiltration. Concentrate supply of water may well represent sprinkler irrigation. However, temporal variability is ubiquitous in rainfall with clear influence on runoff and erosion estimates. So, these people found that the temporal resolution required for the accurate prediction of infiltration was strongly dependent on the soil type and that its effect was practically negligible for soils with either high or low permeability. So we already know that um, we have different types of soils, and of course it is we can consider that some factors will depend on it, and it really matters. It will depend how the panding time will occur. So on the basis of this literature review, we focus in this paper on the processes of local infiltration and panding occurrence for variable water application rates at the surface of both a homogeneous soil and a heterogeneous one represented by a sealed profile. The importance of the infiltration process in soil, hydrology, and environmental sciences had led to considerable literature dealing with experimental observations and theoretical, analytical, numerical, and empirical modeling of infiltration. So back to the topic panding time. As I have said before, panding time is the period of time from the beginning of rainfall until the occurrence of panding. As I have as I have said before. The prediction of infiltration is important in the field, especially for us civil engineering, as our future job is related in on land and type of soils. It is important for us to know the type of soil in a particular place to be able to know how are we going to apply the principle we should apply or principles we should apply. By predicting the time of panding during infiltration, we can be able to know the type of soil in that particular place, and so we can study and know uh, know what to so we can so it is fundamental in hydrologic prediction of flood and erosion. Also, prediction of panding time is fundamental in agricultural irrigation because this is where we will depend our plans and what to apply to execute it. So in this time of panding or panding time, this is all I've got about the concept of this topic and why this topic panding time is important for us. So to continue this topic, one of our group mates will discuss the process how to predict the time of panding. So that's all. Thank you.
So, hi. Before we proceed to this conversation or discussion, let's just have some recap or review about the previous discussion about panding time. The definition of this, what does it mean? Okay, when we talk about panding in hydrology, it refers to the instance when a land surface becomes saturated from rain and panding of water occurs. Yes, so basically, nagkakaroon lang po tayo ng panding if in case yung rainfall or yung precipitation rate is already equal or greater than the infiltration rate. Okay, ibig sabihin kapag nagkaroon ng precipitation or rainfall, kapag na-overwhelm na yung soil and hindi na kaya ng infiltration capacity niya, that's the time nagkakaroon na ng panding. Okay, kasi marami iniisip na agad-agad. Yung panding time is instantaneous. No, hindi siya agad-agad nangyayari. Well, in fact nga, kaya tayo nagka-calculate yung about dito sa gagawin natin. I will show you the calculation on how to get the panding time. Kaya natin siya hinahanap kasi nga hindi siya agad-agad mag-start. Well, not unless kapag sobrang malakas na storm na yan, diba? Kasi it is feasible na mag-zero na yung panding time since once bumagsak agad yung rainfall, since storm niya na sobrang lakas, agad-agad ma-maximize yung infiltration capacity ng soil. Okay? So, this is the formula or the equation that we will be going to use. Calculating the time to panding. Actually, this is just a function of the hydraulic conductivity, the suction head, this one, and the increase in soil moisture during infiltration or the change in water content, also the rainfall intensity, initial rainfall intensity. Okay, so that's the formula or the equation that we will be using in this conversation or discussion. So let us now work for an example. Okay. So a certain soil with this characteristic and also an initial effective saturation of 45%. Okay, given this, the question is for a rainfall intensity of 1.5 cm per hour, how long until panding occurs? Okay, so hinahanap po natin dito kung kailan mag-start yung panding given all these characteristics of the soil. So basically, we will be going to use the equation I have showed you a while ago. Okay, but first of all, we have to calculate the change in effective saturation. Okay, from this to this. Okay, so let's calculate for this first. So basically, we're going to 1 minus 45%, which is 0.45 times phi, or the effective porosity given on the above, this one, 0.423 equals, so you may use your calculators. So the result is 0.23265. So remember this value because we are going to use this one later. Okay, so erase this all. Since we already have the value of this, we can already substitute all the given values from this equation. Okay, so the time to ponding is equal to the value of K, which is the hydraulic conductivity, which is 0.05, times 29.22 times 0.23265 all over, this is the intensity, yeah, 1.5 times 1.5 minus 0.05. So the result is, use your calculators again. So the result is 0.156 hours, or 9.4 minutes. Okay, so the first 9.4 minutes of any precipitation that falls will instantly be absorbed by the soil. So ibig sabihin, after 9.4 minutes, doon na mag-start yung ponding sa situation na to. Okay, so far, any question? You may calculate it as well by yourself. So let us then now proceed to the next problem. Okay, so in here, what rainfall intensity will cause ponding after 20 minutes? So i-compare natin sa previous problem. From this problem, given yung rainfall intensity, nahanapin natin kung kailan mag-start yung ponding. While in this second problem, yung ponding time daw mag-start after 20 minutes. Ang hinahanap natin, anong yung rainfall intensity hinahanap natin kung gaano ba kabigat yung kataas yung rainfall rate or yung intensity niya para mag-start yung ponding time after 20 minutes. So, kung isipin mo, medyo matagal compared sa una. Kasi ito, okay. So, to solve this problem, we just have to rearrange the formula. Okay? So, rearranging the formula, we will obtain I squared minus k is equal to time to ponding. Okay? So, this will be then the formula. Ito po yung gagamitin natin para masolve yung second problem. Okay. So then substituting the values for that using the formula that we have obtained. I squared minus I k is equal to 0.05 29.22 and the delta is 0.23265 all over time to ponding, which is 20 minutes. So if we convert natin siya into hours, 0.333 hours. Okay. So you may use your calculators to solve this. Kailangan natin mahanap yung solutions or roots nito. So for the other should be 9 times Q. Use your calculators. So the final answer is there are two roots. Okay. Of 0.986 cm per hour and 1.036 cm per hour. Basically, this is your density. Okay. Well, actually, if you would observe, if the ponding time takes longer, then the intensity is gonna be lower. Okay. So, any questions so far about this? Hopefully, you may explore it all by yourself. Do not limit yourself about this topic only by this presentation. Okay. This is just a simple and a very brief explanation and a very limited, truly limited discussion about this topic. You may also find some sources to further deepen your knowledge about ponding and infiltration as well. Okay, so I really hope that you are able to understand conceptually these things. Why is this happening? Okay, because it's going to give you the ability to use numerical models. Okay, if you don't understand these fundamentals of hydrology, then it's it's so easy for you to make strong guess when you're setting up numerical model. Parang samba ka na nun. Okay, so that would be all. Thank you for listening.
Good day, everyone. My name is Steven Avila, and welcome to the last topic to be tackled about infiltration. Fitting infiltration model into infiltration data using Excel. Okay, so expected na throughout this topic, we will be using Excel and dealing with infiltration-related problems. And I want to tell you that the references and sources about this topic is quite limited. For me, what I'm trying to say is, do not limit your knowledge about this topic on what I will be going to present or provide to you today. You can do your own research, or you can ask me some questions if I'm able to answer it after this presentation. Okay, so let's start. Have you ever heard in some work, uh, in some work, sa mga jobs, tinatanong nila ang isang applicant if they can use Excel. It's one of the requirement na marunong gumamit ng Excel. Bakit kaya? Like for example, in this infiltration problems, di ba pwede naman sigurong gumamit ng scientific calculators? Mas madali. Mas madaling gamitin ang scientific calculator kaysa Excel. But, when dealing with models and equation, Excel can make your job more efficient. Bakit? Because it can handle both equations and table of data. Furthermore, you can create charts and graph in which way you can interpret the numerical data presented in easy way. Like for example, you have given a lot of data, numbers, and you want your people to understand it easily. You can make graph. By using graph or charts, they can say, ganun pala, ganyan pala yun, bumababa, tumataas. No pun intended. So, Excel is one of the tools in engineering. Not only in engineering, but you can use it in any courses. It is powerful tool in every courses. Okay, let's start in Horton's model equation. So, I've guessed that before this video will be presented to you, the topic about these equations were already discussed by my group mates, so I'm not gonna discuss it further. I'm just gonna show you how to solve some infiltration related problems using Excel. Okay, this is the equation. I know you're familiar with it already. Fp is equals to Fc plus F naught minus Fc times e raised to negative kt. But I want to show you this chart. This line is the infiltration rate. The infiltration rate of some of a material which is saturated is always decreasing. But we have this dotted line which we call the minimum infiltration rate or the steady state infiltration rate of a certain material. Kahit gaano pa katagal mong ilublob o buhusan ng tubig o ibasain ang isang material, once it reaches the minimum infiltration rate, it will not absorb any liquid or water. Okay, so let's do some example problem. Okay. Determine the parameters of Horton's equation and the final Horton's equation given the data below. We have given the time and the infiltration depth or the cumulative infiltration depth. Okay, supposedly I will present you the real-time presentation of the Excel, but unfortunately my material has some problems that I can't show the user form, so I've already pre-recorded the video. Let me show you. Wait, where's it? Okay, this is the pre-recorded video of what I have did in Horton's. Well, okay, let's play it. So first, generate data. Kasi kung mag-real time akong present itong Excel, these user forms cannot be shown in the screen for somewhat reason that I can't understand. And so I chose to pre-record it before showing it to you, okay? So just inputting datas, okay? Let's forward a little. Tell them that, as you can see, all the data that I'm inputting is just the R and the infiltration or cumulative infiltration, which is given in the problem. And after clicking the next or the button next, it already got the time interval, the incremental depth interval or the cumulative depth interval, and the infiltration rate in this time. Next. Okay, finish. Now, let's pause a bit. It said input the final infiltration capacity or the minimum infiltration capacity. Ano yung final infiltration capacity? Well, paano natin malalaman yan? Dito natin titingnan sa infiltration rate box. Look at this at the bottom. 3.243, 3.23. Almost the same. So, malapit siya sa steady state niya, but ang given has hanggang 2.167 hours lang. If we proceed furthermore, we can get a steady state, but we can assume na already na ang steady state niya is 3.2. So we're going to use 3.2 as steady state of this process. 3.2. Okay, and then okay, so let me pause again. So this macro was created by me, derived from source that I've got in YouTube. But this macro can be made, pwede pa siyang i-upgrade. Kung kayo ang gagawa, pwede pa ninyong i-upgrade. Later, I'll show you the codes of this. Okay. You can see this ln minus ln fp minus fc. Saan galing yan? What do you think? Saan galing yan? So, dito yan galing sa equation na to. Nilipat niya, we've subtracted fc both side. So, nalipat tong fc dito, and then we get the natural log of both side. Getting that, we can get ln fp minus fc is equal to ln f naught minus fc minus kt. So, dun galing yung ln fp minus fc. Saan ba natin magagamit yun? Later on, we'll proceed it by explaining it. Okay. Now that we have data, we are now to create a chart. The chart. Okay. Look at this. This line, red line, presents the infiltration rate. I said kanina na infiltration rate is always decreasing. Well, this blue line is the cumulative infiltration depth of the process. While the infiltration rate is decreasing, the cumulative depth is always increasing. That's the relationship between cumulative infiltration and infiltration rate. Once the cumulative infiltration is rising or increasing, the infiltration rate will decrease. And what is this green line? What is this green line? This green line is the data or the chart of ln fp minus fc. Bakit kasama yun dyan sa chart, sa ginawan ko ng chart? Let's proceed. add some thread line, and check display, equation chart, and R square. Now, yeah, nakuha natin to, yan. Okay. Now, nakuha natin itong equation na to. Look at this. Linear equation. Y is equals to negative 2.9924x plus 3.0481. What can you notice about this equation? It is in a form of y is equals to mx plus b, or the uh, slope intercept form. And saan natin ito magagamit? Magagamit natin tong equation na to in identifying the parameters of this equation given this data. So let's proceed. Oh, by the way, this is the video where I use the macro that I created. Later on in this video, I will show you the source that I've got. Yung ginawa ng source na nakuha ko. Okay? Okay, slope, negative 2.9924. Then the y-intercept, by setting x is equals to 0, you can get the y-intercept is 3.0481. In the final steady state infiltration you use is 3.2. Okay. Next, now, nakuha na natin yung parameters. Parameters of Horton's equation. The k, or the Horton's constant, is negative 2.9924. And the F0 is 24.2686, and the FC is 3.2. Now the final Horton's equation is Fp is equal to 3.2 plus 21.0686 e raised to 2.9924t. Excuse me. Now, let me show you the codes. I guess I'll show you the codes. Yeah. Now this is the code. Oops. Let's. Now yes. Yeah. Okay. At first, this command button click, or you see the I've already set a range of E3. I selected it and then used the command user form 1 that show. In that way, show user form 1. Yep, generate data. That button will show the user form 1. This is the user form 1. Look, this is the user form 1. And next, this is the codes. If you can see, just the names of the cells. It's easy. If you can get this video, you can just pause and look at it yourself to study it. Next. User form 2. Almost similar lang sa user form 1, but there's a little difference about in codes. Okay, and this is the finish button where it will command to show the user form 3. Okay, user form 3 like that. So ilalagay na dyan yung steady state. This is a command button. If you look at this is the part where you will get the lnfp minus fc. Are you wondering why I used log instead of ln? In code in VBA, ln does not function as ln itself. the thing that functioned as ln was coded as log, log, and then open parenthesis, the number or the value that you want to be natural log. What? You get the natural logarithm. It means the log code in VBA is equal to ln function. Okay, you must remember that thing. Okay, proceed. Almost done. We're almost done. Yeah, nag-explain siya, hindi lang natin marinig. Okay. Look, now this is the chart code. So I've just researched this on how to make this. I can't really say na naintindihan ko, but I just copied some codes and then trial and error changed something about this until I've came up with the current charts that I'm using. So let me get back a little. Excuse me. As you can see, this part set co sheet 1. This is the range B15. This is where I want my chart to appear. This is the upper right corner or upper left corner of the chart, and this is the range sa top. So upper left ng B15. And then this is the size, 700 by 300. 700 ang width and 300 ang length. Okay? And this is the name of the chart, infiltration chart. Then true has legend, has title. Hey, I'm not gonna discuss this any further. So let's just forward it. Okay. Now this is the part steady state. So I'm not gonna discuss it here because it can be discussed further. Of how I've got the parameters will be discussed further in as we continue the video. Okay. And okay. What I will do here in this part was exactly what my source, the source that I've watched, did. Okay? Let's watch this. So, mabagal kasi ako mag-type, so I've already copied the datas needed. The time and depth. So, yes. Okay. What is it? Okay. So, time interval is equal, sa una, let's just copy the first, 8.0.83. But sa pangalawa, bakit natin kinapi lang? Because he was just, it was just subtracted by 0. Because ang nauna sa kanya is 0, the time 0. But here, pangalawa, kailangan na natin siyang i-subtract itong 167 subtracted by 0.083, the previous. Then, let's just drag this down. Yeah. Then, sa cumulative depth, let's copy. Kung ano yung ginawa natin kanina, ganun lang. Minus, drag. Okay. Then sa cumulative infiltration naman, equals, divide 0.83, enter, then drag down. Now, nakita na naman natin yung FC, so equals to ln, in parenthesis, fp, this, minus 3.2. Hindi natin ita-type dyan. Drag, now, yeah. Now, nakuha natin ang data, we're ready to create the chart. So, just gathering data. Okay. Now time to create the chart. Okay, the chart scatter and hindi pa tapos because the only thing that we've charted was the cumulative infiltration. We want also the infiltration rate. Okay. So, ganito gumawa ng chart. Select data. Then we can add another series. Ano yung series name? Just infiltration rate. Then X values. Ano X values? The R's. This is the X values for the horizontal. Then the Y values. Yeah. Then, okay. Then add pa natin because we also need this LNFP minus FC. Series name. Just click it. X values, the R, the Y value. Okay. Okay, now that we get it right. Okay. Now, we have to put it on the bottom. Bottom. Now, as you can see, it's almost the same as what we've got in the first. It's the same as what we got using the macro program. Just some random na ayos lang yun. Yan, kuha yung thread line. Thread line. Display. Yan, tulad ng ginawa kanina. Okay, now time to get the parameters. Okay, now let's just type. Yung K, or the Horton's parameter, is equal to the slope. The ln-fp minus fc, f0 minus fc, is equal to the y-intercept, 3.0481. And f0 minus fc is equal to e raised to this. And then f0 is equal plus 3.2. Kaya, nakuha natin yung parameters of the equation. Now, time to get the final Horton's equation. Fp is equal Fc, which is 3.2, plus F0 minus Fc is 21.068. Now let's forward. Okay, that is the final equation. Okay, tapos na tayo sa Horton's equation. Let's proceed to by the way, this is the flowchart I made when I created the macro program for the Horton's equation. First, input the data, solve for the time, input steady state infiltration, calculate LNFFC, generate chart, determine parameters, and final Horton equation. Okay, next, Phillips equation. This is probably the easiest. Okay, this is the infiltration rate and this is the cumulative infiltration, where S is the soil suction and K is the hydraulic conductivity and T is time. By the way, the unit of K is always inverse time. Okay, as you can see, the infiltration rate is just the derivative of the cumulative infiltration. Just the derivative or differentiation. First derivative of cumulative infiltration. So next, this is the sample problem. A small tube with a cross-sectional area of 40 centimeters squared is filled with soil and laid horizontally. The open end of tube is saturated, and after 15 minutes, 100 cubic centimeter of water have infiltrated into the tube. If the saturated hydraulic conductivity of the soil is 0.4 cm per hour, determine how much infiltration would have taken place in 30 minutes if the soil column had initially been placed upright with its upper surface saturated. Okay, let me get the video. Where's the video? Phillips equation. Okay, so here we are. This is the illustration of the problem. First, it was laid horizontally, and then the second one is the problem this was looking for was if it was initially been laid vertically or upright. In 15 minutes, so by the way, the cumulative infiltration when horizontally and vertically upright is different. When the tube is laid horizontally, this is the equation. Ft is equals to st1 over raised to 1/2. While if it's vertically, it needs the hydraulic conductivity. Okay, so first we've got the cross section of the tube is 40 centimeter square meter, and the amount infiltrated after 15 minutes is 100 cubic meter. If we multiply this, we can get the value of cumulative infiltration in this object. Okay, the horizontal infiltration is 2.5 centimeter for 15 minutes. Now let's calculate. I'm clicking it. So what we're looking for is horizontal first. So what we're looking for in this horizontal was the sorptivity of the soil. Sorptivity. So please fill up the boxes, then leave the box empty if it was the parameter calculating. So we have the value of cumulative infiltration, which is 2.5. Yeah. 2.5. Sorptivity will be left blank because it was the parameter that we're looking for, and then the time is 15 minutes or 0.25 in R. Now we get the parameters we needed. The sorptivity is equals to 5. It's the same soil as this um, as this tube, so we were using the same sorptivity in solving this, but here we will solve for the cumulative. um, we were looking for cumulative infiltration. Okay, next. Calculate vertical. What we're looking for is the cumulative, so we're gonna leave it blank. Subtractivity 5. Time is 30 minutes, so 0.5 hours. And K is 0.4 centimeter per hour. Calculate. And we get the infiltration depth, or F of T, or malaking F of T, capital letter F of T, 3.7355906 centimeter. So, mapapansin nyo rin, nakita ko na rin agad yung infiltration rate of this both. Infiltration nitong isa is 5 centimeter per hour, and this one is 3.935533906 centimeter per hour. Now, time to get to see the codes of this macro. So, it's easy, simple. Okay, forward. Okay, simple. If you can see, I've used some nested if then, else if, yeah, yep. mm. Forward. Actually, may bug itong aking uh, code, which is here sa part na to, else. I don't really understand how to use the last part, the else part. So, I just put message box error, expecting that kapag wala tayong nilagay na value sa lahat ng box, lalabas as error, but hindi nangyayari yun. So, it's an error, but I put it there to complete the program. Okay, there's nothing to see here much. Okay. Okay, let's get back. Next. We're proceeding to the green ant infiltration. This is gonna be a tricky one. Okay, I'll introduce you something that is new to you in this part. Okay, I guess. Green ant infiltration model. This is the infiltration depth, and this is the infiltration rate. Okay, delta theta is equals to 1 minus effective saturation times the effective porosity is a delta theta. Proceed. Okay, a silty clay soil has the characteristics shown below. Find the infiltration depth and infiltration rate after 1.1 R and 1.2 R, assuming initial effective saturation at 20% and continuous ponding. Okay, let me just find the video. Green out. Okay, here we are. I've already touched it. I guess in this video I'll have so many errors. Okay, that's a 0.1 R we get. Let me explain a little. Okay, let's get back. So as you can see, the infiltration depth have two columns or rows. Okay, whatever. This is the F of T and this RHS or right hand. So in this column, we will assume the value of FT. Bakit? Kasi ang formula ng FT is implicit. We're looking for cumulative infiltration, but the formula needed a cumulative infiltration right here. So we will be using solver in this equation. But how to assume the value of Ft? Let's assume by multiplying the hydraulic conductivity times the time. Okay? Okay. And it's hydraulic conductivity as the time 0.1. Then, okay. Oh, wait. Oh, sumabra ako, sumabra. 0.1. Faster, please. 0.05. Okay. And 0.2. Okay. Yeah. Okay. Now, we've got the assumed value or the guessed value of Ft. Now, time to put the equation. Baka nagtataka kayo, baka pwede naman sigurong clinic na lang ng equals um, time times k. Nope, hindi po natin pwedeng gawin yun because in solver, kailangan nyo itong baguhin which magkakaroon ng conflict kung ang nakalagay dyan is the cell place, yung mga cell. So, kailangan ang nakalagay natin yan is true value. Okay? Okay. RHS, ilalagay natin yung formula equal to K hydraulic conductivity times time plus suction head plus suction head. I'm so sorry, mabagal po ako mag-type. Times the delta theta times ln parenthesis and then 1 plus the guessed value but hindi natin malagay, so just type J4 is located divided by suction head and divided by delta theta. Okay, enter. Now we get that, pero hindi sila parehas. That's where we'll be using the solver. Okay, wait. Okay, J4. No. So as you can see, the difference between this value and this value is quite large. We want it to be 0.00001 as possible as that is the target. Okay, this we can't drag this down, so we'll just copy the code or the formula, Control C, Control V, and then just okay, papalitan lang ng 5. Okay, enter. Now time to use the solver. By the way, solver, nasa data. Pero kung wala pa kayong solver, pwede mo siyang mahanap sa option. So, dito sa part na ito is naglag ang aking cellphone. Add-ins. Okay. Naglag dyan. So, forward natin. Add-ins. Okay. Then, solver. Okay. Okay. Now, makikita nyo siya dito. Data and solver. Click solver. Then, in this part, we have to set the cell into value. Ito yung kailangan nating cell na to dapat maging value niya is 0 by changing the value of this guessed value. Okay. Kung makikita nyo sa option, bakit solver ang ginagamit natin? Kasi ang constraint precision na kailangan niya, hindi lang basta 0. We have 0.00001. I don't know how many 6 or 7? Is that in 10th million? Decimal? Okay, and then solve. Okay, so we're doing this in this, we're doing the same in this part, but you can see here the difference got little, bumaba na masyado yung difference, and as you can see, magkaparehas na ang value nilang dalawa. That is the function of the solver. By changing that part. Okay, solve. Okay, now parehas na sila. Now time to get the infiltration rate, because use this formula, hydraulic conductivity times suction head, oops, kamali, suction head times the delta theta divided by this plus 1. Then copy the formula and do it here. Okay, just forward it. Okay, nakuha natin yung value ng, this is the infiltration depth and this is the infiltration rate. The question is find the infiltration depth and infiltration rate of 0.1 hours. During 0.1 hour, the infiltration depth is 0.318 and the infiltration rate is 0.606. Now, I guess I've tried to make a graph of here with given two datas only. Like what will be the graph is. Tadan! This red is the infiltration rate and this is the cumulative depth. Bakit ibang-iba? Kasi dalawa lang yung given. Dalawa lang yung given na data. Kung ipoproceed natin to hanggang sa pagbaba, meron pa, patagalin pa natin yung oras, makakakuha tayo ng parehas na chart katulad na nakuha natin sa Horton's model, which is nagko-cross na pa ganyan. Okay? Tapos na tayo sa green amp. Last is the favorite of the professors to quiz about. It's the ponding time. Ponding time is primarily focusing in finding the ponding time, and this is the intensity of rainfall. Intensity of rainfall I, and some other variables are already mentioned in green amp model. Okay, this is the sample problem. The soil characterized below has an initial effective saturation of 45%. For a rainfall intensity of 1.5 cm per hour, how long until ponding occurs? And B, what rainfall intensity will cause ponding after 20 minutes? And C, how much cumulative infiltration during 0 to 0.56 R? Okay, the parameters of this soil is the same as what we did in green amp, just that the effective saturation is 45%. Unlike kanina is 20%, I guess 20%, but this is 45%. So let's go to the video. Ponding time. Ponding time. Ponding time. Okay. Okay, ponding time. Okay, ponding time. Hydraulic conductivity. 0.05, section 29.22. Delta theta is 23265, and the rainfall intensity is 1.5. Okay, that is, we've got the values. The time to ponding is 0.15 hours, or equal to 9.37 minutes. With a rainfall intensity of 1.5 and the given parameters of the soil, after 0.15 or 9 minutes, it will start ponding. Okay, time to answer the second question. What rainfall intensity will cause ponding after 20 minutes? We've been given the value of time. So, may mali ako dyan. Yeah, rainfall intensity, hydraulic conductivity, 05, section 29.22, delta theta 0.23265. Time to ponding is 0.333, or the 20 minutes. Okay, we've been given this 20 minutes. So look at this. It's misplaced. I'm so sorry, but this is the answer. As you can see, merong dalawang answer ang intensity. Ang rainfall intensity pag kinompute mo. Bakit? Because the equation is in quadratic formula. It's in quadratic equation, I mean. So, I've used quadratic formula to solve the value of I. So, expected na meron tayong dalawang value. But here, we will choose here the positive, because rainfall intensity can't be negative. Okay? The positive one. This is the rainfall intensity needed for these given parameters of the soil, this type of soil, to start ponding at 20 minutes. Okay, let's answer this C. So how much cumulative infiltration during 0 to 0.156 R? So, nag-iisip kayo, paano natin i-compute gamit yung formula na to? Wala naman ditong value ang cumulative infiltration. But actually, there is a formula which is given that cumulative infiltration is equals to intensity, rainfall intensity multiplied by time to ponding. But we're not given another, just given a time. We're not given a rainfall intensity and time to ponding. So what will we do is we go to Green-Amt method. We will use Green-Amt method. Okay, Green-Amt method. Let's go there. Okay, yeah. So all we needed is 0.156 hour. But here I just want to show you something about the relationship of rainfall intensity and the infiltration rate. So I'm going to divide it by 4, then add something. So the time I divided by 4. Let's forward it. Yeah. Yep. 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 As you can remember, this column or row is the guessed value of infiltration depth. Okay. Then let's repeat the process. Put the formula. I've checked it twice because I guess I've done it wrong. Okay, RHS, putting the formulas. Oops. Uh, okay. Now time to use the solver again. Solver. Set value to 0 by changing. Oops, wrong. That one. Go solve. Okay, return. Okay, let's forward it. Now we can get the infiltration rate. By the way, all was asked in that question was what was the cumulative infiltration after 0.156 hours. This is already the answer. 0.331 centimeter. This is the answer already. But I'm just going to show you something about the relationship between rainfall intensity and the infiltration rate. So I'm gonna find the infiltration rate. Okay, this is the infiltration rate. Now we're going to copy that. Copy. Copy here. Okay. And yeah, okay. Then let's assume that the rainfall intensity during that time is 1.5 centimeter per hour. Okay. If the intensity is 1.5 centimeter per hour, yes, okay. Okay. Let's create a chart. Okay. You can see this chart here. This is the relationship between, oops, oh yes, yeah. This is the relationship between the infiltration rate and the rainfall intensity. This is assuming that the rainfall intensity is uniform, and this is the infiltration rate always decreasing. So as you can see, this point where rainfall intensity and the infiltration rate met, that is the time to ponding. So this is uh, this is also to say that when the infiltration rate is equal to the rainfall intensity, that is the time, or the time that the infiltration rate is equal to the time, or to the infiltration the rainfall rainfall intensity, that is the time to start ponding this part. So that's all to cover the time to ponding. Okay. um so that's all the sources and references that I've got. So if you have questions about this topic, you can chat me using my messenger account, or you can uh, email me. I didn't give the email address I have. Or you can research further about this topic and share it in the class. So that's all. Thank you.